Hey kids, today we're going to talk about a separable differential equation, or separable diff EQ, and these crop up a lot in real life, and I know real life for us right now is like hard, but this is a foundation for where you're going to go as you get into college and narrow your field of study down. Calculus is that base part that sends you off the springboard into the really cool engineering places. Okay, and so along those lines, we're going to talk about a separable equation. And what that just simply means is we've got x and y variables running around. We've got to get them separated so that we can solve a diff EQ. All right? A differential equation, remember, is an equation that has a derivative in it of the form dy dx is equal to f of y times f of g. There you have your two different variables, y and x. And this is called separable. We will need to separate the variables by writing them differently, but still maintain equality. So this steps back to old school Algebra 1 stuff, where you had to isolate one variable on one side of the equation and one variable on the other. Our equations won't be as neat, but it's still the same thought process. The whole whatever you do to one side of the equation, you have to do to the other. And now our bag of tricks includes derivatives and integrals and what other mathematical thing you can think of that you need to do. So the solution is found by anti-differentiating each side with respect to its corresponding variable. All right, so solve for y. If y equals dy dx is equal to xy squared, and it goes to the point 1, 1. So basically what we have to do is we have to get x and y together on each side of the equation so that we've got some shape of this form right here, where we've got y on the left and we've got x on the right. So if I'm going to do that, what I'm going to do is I'm just going to multiply both sides by dx. So dy equals, now watch this, I'm also going to distribute this x squared. dy equals x squared y squared, okay, dx. And in order to continue along separating variables, I'm going to divide both sides by y squared. Okay, and what this gives me then is 1 over y squared. You know what? Let's be cool. Let's call this y to the negative 2 dy equals x squared dx. Okay, and so from here, what we're going to do is just integrate both sides. Now we've got y dy, x dx. We can integrate these. And remember, when you integrate, you're going to add 1 to the exponent and divide by the new exponent. So on the left, I'm going to get y to the negative 1 over negative 1. And on the right, I'm going to get x cubed over 3 plus c. Hey, that's not too bad, okay? So what they want to know is figure out what, if we go through the point 1, 1, what's happening? Well, another way to think of this equation is that we're working with 1 over y, negative 1 over y, equals 1/3 x cubed plus c. And I think one of the most difficult things to remember when you're in calculus is that anytime they give you a point, they're telling you, hey, x is this, y is this. And I think it's really easy to forget that. So when I make that substitution in for x and y, I get negative 1 over 1. And that's going to be equal to 1/3 times 1 cubed plus c. In other words, negative 1 equals 1/3 plus c. And when I subtract 1/3 from both sides, negative 1 minus 1/3 is negative 4/3. So when I get done and I write this equation out, what do I end up with? Well, I end up with negative 1 over y equals 1/3 x cubed minus 4/3. Okay. The thing is, with this equation, we don't really want to leave it as 1 over y. That's not necessarily solving for y. Remember, anytime we solve for y, if we solve for y, we're going to have an equation that says y equals blah, 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 blah. Okay? So why don't we look at this guy by kind of combining everything together in one fraction. So this would be x cubed, because with the denominators the same, it's 3 in both. So x cubed minus 4 over 3. Okay, so this is what negative 1 over y would equal. And if this is a true statement, then I can get rid of the negative by moving it to the other side. So now, gosh, I'm running out of space here. So now this is going to give us 1 over y equals negative x cubed plus 4 over 3. And to deal with the reciprocal part, so I can just have y equals, I need to get y in the numerator. And to do that, I can just use the reciprocal. And if I reciprocal one side and reciprocal the other, I'm legal. So I should end up with an end at this guy right here. Y equals 3 over negative x cubed plus 4. Or another version of this that would be equal, which would be like negative 3 over x cubed minus 4. So anyway, that's how that guy would look. That's how separation of variables looks. It's a few steps here, but it's totally doable. You just got to get the y and x together on their own sides of the equation, integrate, and then make it just say y equals. All right? All right, so let's talk about how separation of variables works with our differential equations, kind of more real-lifey here, but here we go. Remember how exponential growth and decay works, where you've got y equals some initial value a times b to an x power, where a is the initial amount, b is the exponential constant, so it grows if that x is greater than 1, or if b is greater than 1, it grows. If b is less than 1, it decays. And the related differential equation for this is dy dt, okay, the change in y over the change in time equals k times y, okay? And this is where k is growth or decay. So let's solve out this differential equation. And this is going to require a little bit of a leap of faith from some of you guys. Kind of follow along here, and if you don't understand everything that's going on right away, that's all right. It will start to make sense as we work through some of these problems. So here I've got dy. This is really bad handwriting. I don't know what's gotten into me here. Maybe I'm hungry. Let's try this again. Okay, so dy dt is equal to k times y. Remember, k is just going to be some sort of constant, okay? Well, what we need to do is we need to separate these variables. Notice I have y over here and y over here. I've got to get y's together, which means dt needs to go to the other side. So I'm going to take a 2 for the price of 1 step here. I'm going to divide both sides by y, multiply both sides by dt. Now watch here. This is really cool. dy over y equals k times dt. Did you see that? Did you see that? Okay. This is straight out of Algebra 1 101. All right. So dy is actually going to be, maybe an easier way to think about this is 1 over y dy equals k dt. Okay, now integrate both sides. All right, and this is going to be a little bit on the weird side here, but just work with me because we're headed someplace grand. Remember, the derivative, the antiderivative of 1 over y is natural log y. And remember that the natural log only works if the absolute value of y. Okay, it's got to be positive. That distance has to be positive. And that's going to be equal to k times t, okay, plus another constant, okay? So two things now. This constant can be anything right here. And even though we integrated this side, this constant takes care of the possible constant on the left. Okay? I know it's weird. Just hang in there. It will all be okay. Now, I've got to undo this natural log because remember, we're solving for y. And the way that you can undo a natural log is by using the exponential function. So basically what I'm going to say is I'm going to go e and e. All right, just like this, e to this power, e to this power. This is an equality statement. I'm doing it on both sides. There's been no cheating going on. And what that's going to give me then on the left is absolute value of y equals e to the kt plus c. All right. Again, I know this is different and perhaps a little strange to think about how to solve a problem like this, but it's totally on the up and up. Now, keep in mind how the powers with exponentials work. Notice down here I've got e to the kt plus c. So what I've got is e to the kt times e to the c. Okay? And remember, I can do this because if the bases are the same, then I add the exponents. Look what I'm doing down here. I'm adding exponents. The bases are the same, so I can multiply those bases together. Now, let's address this whole absolute value thing. Remember, absolute value says we've got to be either positive or negative. It doesn't matter too much. And so the next step on that would be to change this C part to account for the positive or negative. So this is going to look really weird, but hang in there. Y equals plus or minus e to the c times e to the kt. All right? Again, I didn't do anything crazy. Remember, if we take the absolute value of this guy, we're going to have positive e to the c or negative e to the c. And if we take absolute value, we'll always get that positive version out. Well, this should start looking familiar to this guy right here. Notice, this is a constant. This is a number. This will be our initial value. So we will actually end this guy. We will let A represent plus or minus e to the c. So our solution for this differential equation will be y equals A times e to the kt. Now, that we've seen before. E is our base, k times t is our exponent, and I just think this is a really neat thing to do and understand because the next few problems that we work out are going to be based off the formula that we just discovered. All right, so keeping in line with our previous example and talking about how the differential equation is equal to a rate of change, all right? Then what we've got here is a little bit of a different form of that. dy dt equals k times y, where y is going to become y0 when t is equal 0. In other words, y0 is your initial starting amount. So if we apply everything we did on the previous slide to what we're getting ready to talk about here and make this substitution with k and y0, then you have that y, okay, your total amount, is equal to your initial value times e to the kt power. K is a constant, it never changes. T changes, your initial value doesn't change. So what we're going to be able to do with this is identify a way to keep track of money that's growing in a bank, for example, or something that grows exponentially, okay? And what we're going to look at with this next example is specifically money in a bank, but you could use this to find how rates of change occur with different bases, how something, different fungus or whatever, or mold multiplies and grows. There's all kinds of different ways that you can use this, okay? So continuously compounded interest involves E, and if you have interest that's compounded at different set periods of times, that would be referred to as the K. All right, so let's look at this continuously compounded interest part. If you invest a sub $0 or an initial amount of dollars, notice this is very similar to our previous problem, our previous rule from right here. Okay, if you invest a $0 into an account with a fixed annual interest rate R, and if the interest is compounded K times a year, then the amount of money represented after T years is going to be this equation right here. So we're going to use this equation a lot in the next few minutes, okay? But there's different ways that we would figure compounded the interest continuously, okay? So we can model growth of our money with a differential equation that has this initial value. So here's our differential equation with our initial value, and when we follow the path down, just like we did on our previous problem, if we follow this path down right here, what happens is we end up at this problem for finding the amount of money after t years. So we solve the differential equation, we substitute in our initial condition, which was that t is equal to 0. And what happens is we end up with this formula down here for continuously compounded interest. Okay? So now the question becomes, suppose you deposit $800 in an account that pays 6.3% annual interest. How much will you have after 8 years if the interest is compounded continuously and quarterly? So we would set up with y equals A0 EKT for part A. All right. And for part B, we set up with y equals A0 times 1 plus the rate divided by K to the KT power. Okay? So these are the setups for these. And we're told the rate for both of these is going to be 6.3%. Well, we have to have our rate as a decimal, so 0.063. Same for this guy, 0.063. Okay? And we know that our initial value is $800, so A0 is equal to 800. Okay, so how much will you have after 8 years? Well, we've got this set up. One last thing, T is 8. I don't know why my tablet's making those wiggles. I don't feel like I'm writing that way. So now what we have to do is get your fancy dancy calculator out, plug these values in, plug them in carefully, and see what you get. So in this case over here, we'll switch it up a little bit in pink. Y equals 800 times E, and then for the exponent, 0.063 times 8. So I'm going to punch that into my calculator real quick. We'll just work these bad boys out one at a time. So here we go. 800 times E.
Thank you for saving my cup.
800 times E to the 0.063 times 8, which is going to be $1,324.26. That's how much we would have after 8 years if we just start with $800. Okay. On the next guy, we'll solve him out in purple. What we're going to do is we're going to say that y equals 800 times 1 plus the interest rate 0.063 divided by K. That's the number of times that we're going to compound interest, which is 4 times a year. And then we're going to raise this to the 4 times 8 power. So I'm going to punch that in, and we should get a number that's similar, but not the same. It should be a little bit different. So 1 plus all right, and on this guy over here, we end up with $1,319.07. So, interesting story here. There's not a large difference between these two, even though one interest is compounded continuously and the other one's only compounded 4 times a year. But this is how you would look at some of those different rates of change, starting from the differential equations that were at the beginning of this lesson. Radioactive decay is really similar to our law of exponential change. The one thing now that is going to happen every single time with decay is that K is going to be less than 0. Remember, K is some constant value, and K is going to be less than 0. So I know if you're looking at this looks weird, okay? But think about what's going on. I need K to be negative. So if K is greater than 0, I have a negative value here. Okay, if K is less than 0, I have a negative value here. So it looks funny, but it's true. All right. So half-life then. Find half-life. This is the amount of time required for half of a radioactive substance to decay. So if the half-life of, equation, find the half-life of a radioactive substance using the decay equation, y equals y0 e to the negative kt, and show that the half-life only depends on k. Here's the thing. If this is my starting equation right here, then y0, just like in our previous example, is an initial amount. And so if my initial amount is going to be half of that, then the equation that I'm going to look for is that 1/2 y0 is equal to y0 times e to the negative kt. That's the setup on this. And so if I'm going to try and solve this guy down, if you'll notice right off the bat, I can divide both sides. I can divide both sides by y0. Divide this by y0. Divide this by y0. Okay? And when I do that, what I end up with is 1/2 equals e to the negative kt. Okay? Not bad, not bad. But I've got this whole exponential issue going on. So one of the cool tricks that we can use is you can take a natural log of both sides. And when I take a natural log of e, it undoes itself and leaves me with just kt. When I take the natural log of 1/2, I get natural log of 1/2. So natural log of 1/2 is equal negative kt. Okay? That's not too bad. So remember, we want to show that half-life depends only on k. All right? So what we should try and do then is get this equation to say like t equals or something along those lines. So if I'm going to do that, all I'm going to do to kind of get where I'm going to finish this guy is just divide both sides by negative k. So negative natural log 1/2 divided by k equals t. Okay, well, that looks cool and all, but there's one more step, and that is this. If I am looking at 1/2, that's the same thing as 2 to the negative 1. And if I have a logarithm where I have 2 to the negative 1, that's the same thing as taking that negative 1 and multiplying the logarithm. So to finish this whole problem, I would do that by saying that I've got negative this guy, negative 1 times the natural log of 2 all over k equals t. And that's where we're at. So simplify this up and you end up that the natural log of 2 divided by whatever our constant is for our problem will tell us the amount of time. And once you solve out this differential equation and you look at it, k is the only thing that can have an impact on half-life. And once we know what that k value is, we can determine the amount of time it'll take. And that's what this problem is showing us. It's really cool. And it can be a little bit confusing at first. But the key thing here is that the initial value doesn't matter because it divides out on the very first step. All right, let's explore an exponential function now with a base that's different than e. Sorry about that. So what we're going to do is we're going to look at a hornet's nest. We're going to look at a population of 10 on May 1st. The number of hornets grows to 50 in 30 days. And it says that they're growing at a rate proportional to population. So when I look at that, what I'm seeing is I start with 10, I stop at 50, and this reduces to 5. This is my proportion that I have to have. This is my value of B. I've got some lag here, sorry. All right. Now, that's B. I have an initial population of 10. That's Y0. Okay? On May 1st, the number of hornets grows to 50 in 30 days. Okay, we got that. If the growth continues to follow the same model, how many days after May 1st will the population reach 100? Well, we want to know T. We don't know. All right? T, we don't know. we know that we end up with a population of 100. And here's the H part. Did you see H in there? It takes 30 days to go from 10 to 50. Okay? And remember, this is proportional. So at the end of that 30 days, we've succeeded in growing one time. All right? So that means that H is going to be 1 over 30. All right? So here's what my problem is going to look like. 100 equals 10 times 5 to the 1, what the heck? 10 times 5 to the 1/30th times t. All right, t is what we're interested in. So divide both sides by 10. And when you divide both sides by 10, you get 10 equals 5 to the t over 30th, t over 30 power. And the only way to handle this is to natural log both sides. And remember, when we do this, what happens is I get the natural log of 10 is equal to the natural log of 5 to the t over 30 power. Well, any exponent inside a logarithm can be written outside the logarithm using multiplication. So natural log of 10 equals t over 30 times the natural log of 5. Hey, we're making some progress here. Divide both sides by the natural log of 5. So the natural log of 10 divided by the natural log of 5 is equal to t over 30. And then you'll notice that I can finish this off by multiplying both sides by 30. So 30 times the natural log of 10 over the natural log of 5 will give me t. And when we do that, you're going to end up with 42.92 days. So there you go. A little exponential growth with a base other than e. All right. In this example, we're going to look at some more exponential growth and decay type of situation here. Real life-ish, kind of, if you died 5,700 years ago, real life. So scientists are using carbon-14 dating, which uses 5,700 years for its half-life. Find the age of a sample in which 10% of the carbon originally present has decayed. So the formula that we're going to stick with is the one that we've kind of been using, which is, let's see here, y equals that initial amount. And in this case, we're talking about half-life. So our base is going to be b. And if 57 years is half-life, that means after we go 5,700 years, we will have lost half. So for our exponent up here, we're going to talk about t over 5,700. Okay, and t would be the number of years. So this is the setup for this particular guy. Well, scientists are going to use carbon-14 dating. All right, we've got all that. 5,700 years, got that. Find the average age of a sample in which 10% of the carbon originally present has decayed. Okay, 10% has decayed. So basically what we're saying here is 10% of our original amount is left. So we've got 0.90 or 90% of our original amount left. Okay, that's how this problem is going to set up. So we're going to substitute all of these things in here, where you're going to have 0.90 times our initial amount is equal to our initial amount times 1/2 to the t over 5,700 power. Okay, not hard, not hard. Now, solve this guy out like you would an algebra problem, and the first thing that we want to do is kind of clear off all the things that are on both sides together. So I can actually divide by the initial amount, and looky here, the initial amount actually cancels out on both sides. So as it turns out, he's not important when we're trying to solve for t in this situation. And the reason is because we're looking at a percent of the original amount left over. Okay, if we had a different y, then this wouldn't work. Okay, but since we're talking about the initial amount the whole time, that's not a problem. So 0.90 equals 1/2 t over 5,700. Okay, now take the natural log of both sides. Okay, so the natural log of 0.9 is equal to the natural log of 1/2 to the t over 5,700 power. And when you do this, anytime you have an exponent inside a natural log, anytime you have an exponent inside a natural log, you could take that exponent and move it to the front of the natural log. So natural log of 0.90 is equal to t over 5,700 times the natural log of 1/2. Okay, and again, we're trying to get the t all by itself here. So we would multiply both sides by that 5,700. And then we would have this. So we would have 5,700 times the natural log of 0.90 equals t times the natural log of 1/2. So I can finish this then by dividing both sides by natural log of 1/2. And when I do that, I get the age of a sample in which only 10% of our carbon has decayed. So let me just punch that into my calculator real quick. And what I get is 5,700 times natural log 0.9 divided by natural log 1/2. I get 866.418 years. So that's about how long it would take this 1/2 to work. And this problem isn't really too bad, and it's actually the part that we're dealing with isn't too calculus-y. This is almost like a rewind of pre-calculus and really manipulating your logarithm rules and working with those. The trick here, though, is dealing with that initial amount. It cancels out. It doesn't always. And so just because we do that this time doesn't mean we do it every time. However, when you're dealing with original amounts and percents of original amounts, in the end, you don't need to know that because that's what we're trying. It just cancels out. It goes away algebraically. Okay, so there you go. Carbon-14 dating. All right, let's look at a pretty interesting law now called Newton's law of cooling. And this is really a fascinating thing, the way it works. And the people that figured it out, brilliant. We're going to really look at it now and examine where it comes from and how it works. So if we've got hot coffee at room temperature, water that's overheat, a cake just from the oven, all these things follow Newton's law of cooling. So the coffee that I'm drinking right now came out of the spigot and into my cup, really hot. But right now it's not as hot as it was when it first came out. So what's happened to it? It's cool. And believe it or not, it's cooled based on the surrounding temperature of my classroom, and it's cooled based on the fact that it's no longer being heated. It's just sitting here on my desk. So it follows Newton's law of cooling as it does this. Like, I can take the coffee, if I know what the coffee's temperature is, out of the coffee pot into my coffee. I can set it down, and if I can determine the temperature of my room, I can figure out how long my coffee will take to cool to a temperature that I can drink, and then cool even more to a temperature that I don't care for. So what we have is this differential equation, the change in temperature divided by the change in time. And remember, when you're talking about change in temperature, we could say this right here, that dt, that's the top of this fraction, dt is equal to the change in time, which is your temperature of your item minus the temperature of the surrounding area. Okay, and so if we know that, then what we have is we can rewrite this equation right here, which is going to become d dt of t minus ts. And that's going to be equal to negative k times t minus the surrounding area, which is ts. And so we can, again, go one step further with this and separate our variables and do all our integrating. But we're basically, what we're using is our law of exponential change. And so let's just rewind real quick. Law of exponential change has this shape. Y equals the initial amount, e to the kt power. Okay? And so back to Newton's law of cooling, what this does for us, what this guy does for Newton, is it takes our original initial amount, okay? And for us, our original initial amount is going to be that original initial change in temperature, okay? And so our problem then, if we follow what we've done over here previously, what we've set up, we're going to integrate, we're going to separate variables, integrate, and it's going to have this shape, right? And so what we end up with is this, T minus the temperature of the surrounding area, because if you integrate this side, that's what you get, is equal to T initial, all right, or the initial temperature minus the temperature of the surrounding area, okay? And then our E, K, T. And in this case, our K will have a negative sign in front of it because we're talking about a decay situation where temperatures are cooling. And so if you just follow the steps that we've taken previously, we can get to this equation, all right, from this differential equation. And if you want to sort that out on your own, that's fine. For me, for what we're going to do, I want you to just to see that there is a relationship here. Look, lots of things are the same. Look how lots of things here are the same. I want you to just recognize the similarities between these two items, okay? We don't necessarily need to prove all this in class. I just want you to understand, look, this is a differential equation. We are solving it out. We are going to use integrals and all that kind of thing to get to Newton's law because we're examining the change. So what we're going to do is we're going to take Newton's law of cooling here and we can actually apply it. Ts is the surrounding temperature. TO is the initial temperature when my coffee comes out of the coffee pot. And T right here, this T is my final temperature over a certain amount of time. So this is a really complicated equation. Let's check it out. Use our new equation, T minus Ts is equal to T sub 0 minus T sub s e the negative kt, and solve this question. A hard-boiled egg at 98 degrees Celsius is put in a pan under running 18 degrees Celsius water to cool. After 5 minutes, the egg's temperature is found to be 38 degrees Celsius. How much longer will it take the egg to reach 20 degrees Celsius? Well, here's the deal. T0, our initial temperature, is 98 degrees. Okay? The surrounding area in this case is the 18 degree water. So Ts is equal to 18 degrees. All right. We're told that our time is 5 minutes. And then we're told that after that time, the temperature of the egg is 38 degrees. All right. We've got enough now to get started with our Newton's law of cooling. Okay. All of these things up here are going to be used. We're going to use all of these guys. We're just not going to use K. We're going to discover K, because as we discover K, we're going to find the relationship for this particular problem. Okay? So 38 minus 18, and I'm just substituting into Newton's law that's written right there at the top of the page. The initial temperature, 98, minus the surrounding temperature, 18, times E to the negative 5t. Okay? So 38 minus 18 is 20. 98 minus 18 is 80. Divide both sides by 80, because what we're going to try and do is get that E all alone. So we're going to end up here with 1/4 equals e to the negative 5t. We're going to take the natural log of both sides. Natural log allows us to get rid of the e. A natural log of e is whatever the exponent is. In this case, it's 5t. So when I natural log both sides here, natural log, I end up with the natural log of 1/4 equals negative 5t. Divide both sides by negative 5. And we find out, this should be k the whole time. Gee willikers. This should be k. 5 is our t. We already knew that. So k. All right. So pause video real quick. Punch this into your calculator. See what you get. See if it matches mine. I'm going to do that right now. And I get k to be 0.277. And I'm going to go ahead for accuracy. I'm going to go ahead and carry it out one more decimal place. 2773. And now what I'm going to do is I'm going to take this guy and substitute him back into this equation, because now I want to know how long will it take the egg to get to 20 degrees Celsius. So all of these numbers change now. Not all of them. So my original temperature is 98. The temperature of the surrounding is 18. Time is now something I don't know. But my final temperature now is going to be 20. And by the way, we discovered K is going to be 0.2773. So I can use this equation again, Newton's law of cooling. I'm going to do it one more time. And this time I'm going to solve for T instead of K. So it's all the same things that we just have worked out. This time, T instead of K. 98. Let's see, back up. 38. Let me back up again. Gee willikers. 20. The temperature that we're interested in. Minus 18. The temperature of the surrounding area is equal to the starting temperature minus the temperature of the surrounding area times e to the negative k, 0.2773 t. All right? And there you go. That's the setup for this guy. Now we just follow our math. 2 equals 80 e to the negative 0.2773 t. So divide both sides by 80, and that's going to be 1/40 equals e to the negative 0.2773 t. I'm getting low on space here. Take the natural log of both sides. And when you do that, you get the natural log of 1/40 is equal to negative 0.2773 t. And just divide both sides by that negative 0.2773. So pause the video real quick if you want, or whatever, and punch that into your calculator. See if you can get what I get. And I got 13.3 minutes. So there you go, Newton's law of cooling. Got to solve it twice to get your ultimate final answer, which is this bad boy right here.